Okay, kids, now we know a little bit about the concept of half-life. Let's go into some sweet, more awesome problem solving than just basic ones. No, please don't. Billy, it's not the attitude we want here. Okay? Oh, okay. That's better, Billy. I'm ready. Billy, well done. All right, like it. Now, it's all about the attitude, people, all about the attitude. Half-life problems can be relatively easy. So if I said you got a 100-gram sample of radioactive material, it undergoes 4 half-lives, how much is left? And you cut it in half 4 times. So 50, 25, 12.5, 6.25. Okay? The other thing is you have 1/8 of it left because 4 half-lives, 1/2 times 1/2 times 1/2 times 1/2, 1/8, 2 times 2 is 4 times 2 is 8 times 2 is 16. You have 1/16 of it left. Okay, strike that. So 1/16 of it would be left. So 1/2 times 1/2 times 1/2 times 1/2. So do the math. 2 times 2 times 2 times 2. So it's 1/16. If there's 5 half-lives, times 2 again, so 1/32. So 1/32 of it. All right, so that's how that works pretty easily. Or if I said the half-life is 10 days, how much of the sample is left after 30 days? You know to cut it in half 3 times. 30 days, 10 days, 10 goes into 30 3 times, that'll be 3 half-lives. So cut the sample in half 3 times. Relatively easy. Sometimes problems are like that. That shows the concept, but sometimes they're not. What if the half-life is 28 years, and I want to know how much is going to be left after 3.5 weeks? Okay, so we need to get from where we are here to there. Okay, but before we do that, we have to talk about what's called decay constant, activity of a sample. So the radioactive decay is the amount of breakdowns per second. I have a breakdown like every week, okay? Okay, usually every Friday afternoon I have a breakdown. By then I recover over the weekend and I'm good to go, all right, by Monday. So a decay per second, one breakdown or change, it's a change. We call it breakdown, but it's a change. So one change of something radioactively giving off gamma or alpha or beta and changing. Although the gamma doesn't change the actual element itself, it just makes it a little bit more stable, less energetic. Remember that, okay? Yeah, so gamma is not a particle. But if a particle is given off, you change it literally into something new. And, I'm gonna rock your world. Are you ready for this? I forgot to rock your world in the video a couple of videos ago. I rocked your world once and told you there was a thing called a positron. Did you check it out? You should. Don't believe me. Again, this is where I went to college. You don't want to trust anybody who went here. Okay, I don't know what they're talking about. So look it up, positron, rock your world. Second thing I want to rock your world with is the positron or the electron that come out. They come out of the nucleus. That's right, nucleus. I said it. No, they don't. They're in the energy levels. I learned that in chemistry. Yeah, well, chemistry, remember, is not the apex predator of all the sciences. Physics is. Okay, here you learn the truth. You can get electrons in the energy levels as well, yes, but they also can come out of the nucleus, is where these positrons or electrons, the beta particles, are coming from. Whoa, rocking my world, I didn't know that. I know. And you ready? Rock your world again, one more time, is that a proton can be converted into a neutron and a neutron into a proton, and that's exactly what's happening in the nucleus when you have a beta particle ejected. You're changing one to the other. Whoa, I didn't know that. I thought they were like set in stone. No, they can change, okay? Rocking your world. Yeah, this is fun. See, Billy, I knew you'd come around. It took like a full year to do it, Billy, but you're coming around. I appreciate you now. And I appreciate you too. See, we have a mutual appreciation. Okay, where was I? Oh, talking about breakdowns. Oh, so there are changes. So a decay every second, decays per second. Okay, one decay per second is called a becquerel. A becquerel, abbreviated by BQ, a becquerel. Okay, now, becquerel is 1 decay per second. Or 1 breakdown per second. Or if you have a Geiger counter, we've all seen those in the movies, when you're clicking like that, all of a sudden Godzilla's going to come up and kick the crap out of you because he's radioactive. That's right, that's your Godzilla. Geiger counter goes, pin it. So 1 decay per second, though, that's really not a lot. 1 decay per second. If you were getting hit by 1 decay per second, you'd laugh at that because you're going to hit by more than that. I've measured the background radiation in this classroom many times. The background radiation hitting a Geiger counter is about 1 decay every 2 seconds. Well, the Geiger counter doesn't have a lot of surface area. Okay, you do. Okay, no, I didn't mean to call you. I didn't know. No, so sensitive. Okay, no. So for example, your surface area is up greater than the Geiger counter. So I'm getting hit by a lot of background radiation over my body. I'm like, ow, ooh, that one kind of hurt. Ooh, that was a tough one. So I get hit by becquerels every second, so do you. It's called background radiation, perfectly natural, fine. We're adjusted. We know how to handle that. Yes, we do. I know how to handle them. Okay, yeah. So then when we have a becquerel, 1 decay per second, it's not a high number. It's not a lot of change per second. 1 per second is not a lot. Trust me, you can get a lot more than that. So what we also have is a unit of radiation called a Curie. Yeah, you've heard of her. Madame Curie. Yeah, that's her. And so we'll abbreviate. It doesn't look like I capitalized that, but I did. Okay, so 1 Curie is equal to 3.7 times 10 to the 10th becquerels. Whoa. Yeah, you can laugh at a becquerel. Don't be laughing at no Curie, okay? That's... whoa! Shook me up. Woke me up, though. Curie of radiation. Okay, so this is used for much larger doses of radiation. If you ever watch a movie or something, it might be talking about Curies of radiation. Now, you won't be talking about becquerels, typically. All right, okay. Okay, so a little bit background now. So this is a decay per second. A Curie is a lot of those. Or 3.7 times 10 to the 10th decays per second would be a Curie. This is the International System Unit, the becquerel for radioactive decay. All right, okay, decay. Activity. Activity of a sample. How active is a sample of radiation? Well, that's going to depend on a couple of things. One, how much of it do you have? Are we talking about you got just a little tiny bit of it? Oh, just a little tiny cute bit of radiation. Yes, you are. Okay. I'll take you and put you in my pocket. Yeah, and keep you around with me and walk around all day with you. Okay. Talk about sterilization. Okay. Be careful there. So what if you had a whole crap ton of it? You can carry on that in your pocket. All right, so yeah, it's going to make a difference if I have a lot of radioactive material versus just a little tiny bit of radioactive material. How many becquerels are you going to be, getting from that? So the amount of the radioactive material matters. You know that if you think about that. Okay, if you have radiation spread out over a large area, laugh at it. But if you have a whole bunch of it concentrated in front of your face, you won't be laughing very long. So the amount of radioactive material is going to make a difference in the activity of the radiation. Also, what else is going to matter? The half-life. Some things are very radioactive in terms of they give off these decays very rapidly, very quickly, as opposed to okay, that, not very fast, right? As opposed to, okay, if the half-life is very short, these things are transmuting, there's a word for you, or transmutating very rapidly. So the activity would be higher. So it looks like there are actually 2 things that go into what's called the activity of a sample. How much of it you have, and what the half-life is. Half-life is part of that. Speaking of which, we are now ready for an equation. Yes, we are. I'll get back to activity here just a minute. We'll go back up here and write down an equation. Here we go. Physics, you know they're coming. For half-life. Half-life is equal to the half-life time period of a radioactive sample of something is equal to this number here, 0.693. Calculus derived, 3 on the tree. I was driving. Calculus. over lambda. Lambda, lambda, lambda. Lambda is the decay constant symbol. Now, I didn't say the unit. I didn't say the unit for it. We said it's the decay constant symbol. So this, I'll write that down, is decay constant. It's a number. Okay. So the unit for decays per second is the becquerel. The decays per second, which is the unit of the becquerel, is going to have something to do with this thing here called the decay constant. So there's a number that goes in for this. Now, any physics book worth its salt, which they all are, because it's physics, okay? Apex predator, remember that, is going to have a radiation appendix, okay? Not heart, not liver, but an appendix. Funny. In the back of it, that'll have half-lives. It'll have half-lives in there. Oh yeah, by the way, I looked up the half-life. I was getting my half-life thing confused. In the last video, I was talking about the half-life of uranium-238 and uranium-235, and I was getting my numbers mixed and matched wrong. Uranium-238 is 5 billion years for a half-life, and uranium-235 is 700 million. So I had the 5 and the million in the wrong spot there. So it's 700 million years. So either way, it's a long time, okay? Those half-lives are a long time. It's going to be around for a long, long time, that stuff. And when the Earth goes into supernova, not supernovas, there's that kind of supernovas, not heavy enough. The Earth, the sun, okay, the sun, when it goes in, it won't go into supernova, but it will go into what's called a red giant phase and blow up and envelop the Earth, and everybody's dead. But don't worry, it's not till 5 billion more years. Okay. Oh, phew. Good thing it wasn't tomorrow. I had plans, big party. Yay. Yeah, well, now you have something to celebrate, that you're not going to get enveloped by the red giant stage of the sun for 5 billion years. Woo, yeah, party now. That's good. We're celebrating. Okay, so, yeah, but when that happens, half the uranium is still going to be around. It's not ever going away, ever. We'll talk about that. Okay, now, back to this. So, this symbol, lambda, which shows up a lot, doesn't it? You know, we've seen it before, haven't we? Where have we seen it? Very good, Billy. Yeah, lambda is equal to what's called the decay constant. Now, this has to do with the probability that something is going to break down in the next second of time. So this is about probability, these decay constants. That's what this is. It's a probability number. So when something decays, you know, if you have a half-life of, let's say, 10 days, then you've got a bunch of this sample that's radioactive. Well, if you're watching it, oh, this is exciting, watching this radioactive material break down. If you're watching it, well, there's a probability that in the next second of time, one of those atoms is going to change into something else. Okay, it'll give off an alpha particle or beta particle and become something else. But it's a probability. So you could be watching it for like 5 seconds. Nothing changed. Well, I said it's a probability. We didn't say it was definitely going to happen every second. Let's say the next 5 seconds. I saw 5 atoms change. Because the probability is that there's a certain probability of 1 atom changing per second. Now, the probability of an atom changing per second is very tiny. It's very tiny. These decay constants are very small numbers. You know, they're like 0.0000 blah, 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 blah. Like maybe 0.000007 or something like that, maybe 10 to the negative 4th chance of this atom decaying over the next second. Okay, it's very small. But if you have a whole bunch of atoms, then, you know, the probability of any one of them decaying is very tiny. But if you have a butt ton of them, somebody's going to be decaying over the next second. Radiation is about probability. These decay constants are values. They're actual numerical values that tell you the probability that an atom is going to change into something different over the next second of time. So they're very small. Now, half-life. Sometimes I use the number 0.7 for this. I use 0.7. Don't multiply that by 7. I'm not saying that. It's 0.7. I use 0.6 rounded. Close enough for government work, okay? 0.7. And so, but if you can remember that number 0.693 divided by, now sometimes we need to figure out the decay constant. Usually a book with the appendix will give you the half-lives of materials, and you got to figure out the decay constant. You do. How would I do that? Just switch these. Okay, switch the half-life and the decay constant. So if I want to figure out the decay constant, then I can look up in a book what the half-life of the material is, divided into 0.7 or 0.693, and you'll have the decay constant value, that probability that an atom breaks down per unit of time second. Okay? Now, one other thing to be careful of, though, this has to be in seconds, because these are decays per second. Decays per second mean that's got to be in second. Oh, so if I was like doing uranium-235, then I'd have to take 700 million years and make it into seconds? Yes, you would. A lot of seconds, right? So that's a big, huge number, 700 million years. How many seconds is that? Whoa. You're going to end up with a big number here for half-life in seconds. And you're dividing that into that. This decay constant value is going to be extremely small. Extremely small. I hope that makes sense, though, because if your decay constant's extremely small, that means the likelihood of one atom, you can sit there and watch it. I'm watching you, atom. I'm watching uranium-238. I'm watching you. Okay, remember? Yeah, you know the movie. Watching you. Over the next second, the chance of it breaking down are minuscule, tiny. You might be waiting 5 billion years before finally you broke down. I've been watching you for 5 billion years. I'm very aggravated. Yeah, again, big number. On the bottom, small breakdown probability per atom. It'll take you a long time on average to break down an atom. Now, if you have a lot of atoms, so you have a large sample, somebody's going to be breaking down in the next second, most likely. All right, so sometimes with Geiger counters are interesting. Like we'll use Geiger counters in class, and you'll like not get a click. Nothing happens for 2 or 3 seconds. Nothing, and all of a sudden, click, 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 click. Just probabilities. Sometimes nothing happens. Sometimes things break down really fast. Okay, I've been babbling on a lot in this video, so this video is getting kind of long. What we're going to do is kind of wrap this. I didn't talk about activity yet. So I talked about half-life and decay constants and things like that. Now we'll get into our next video, the activity equation. All right, so we'll get into that next video. We'll stop this one for now. You kids go get a water break. I need one.